This is a quick review on some background equilibrium. So equilibrium is a topic that will be discussed throughout the semester, but these are just kind of the basic background things. We're not going to talk about much in way of calculations, no ice tables, just kind of vocab, remembering how things work. So an equilibrium reaction we will always be able to identify with the forward and reverse arrows. And so when we have an equilibrium reaction, we can always set up the equilibrium constant expression. Capital K is the abbreviation for the equilibrium constant, and then it will have a subscript going with it. So in this slide, it's got a C, which is just telling us we're dealing with concentration. So there are many different units of concentration, but the one used in equilibrium is always molarity. So when setting up the equilibrium constant expression, we take the constant K and then set it equal to the products from the balanced reaction, where the coefficients from the balanced reaction become the powers on top, and then the reactants are in the denominator. And again, their coefficients become the powers. When we're writing the equilibrium constant expression, pure solids and pure liquids are equal to 1, which means we don't see them in the equilibrium constant expression, so we pretty much ignore solids and liquids, but that's just because they're equal to 1. Think about it, pure solids and pure liquids don't have a molarity. They're not, there's no solute solvent, they're pure substances. So the equilibrium constant expression is based on the stoichiometry, so you have to have a balanced chemical equation when you go to write the equilibrium constant. So once you write the equilibrium constant expression, there are many ways that we can go about calculating it, but once you have the equilibrium constant value, if the equilibrium constant is a very, very large number, talking times 10 to the third, times 10 to the fourth, times 10 to the fifth, on up, what that's telling you based on the equilibrium constant expression, the numerator in the ratio is much larger than the denominator. So there are a lot more products than there are reactants. So by the time that reaction hit equilibrium, which is just the point where the forward and the reverse rates are equal, so it no longer seems to be making new reactants or products, although the reaction never stops, but we're at a constant concentration. So at that equilibrium point, there are a lot more products at equilibrium than there are reactants. If the equilibrium constant is a very small number, now it can't be negative, but I'm talking like times something times 10 to the negative third times 10 to the negative fourth, which just means small numbers, right? 0.000 something. What that's saying is the denominator of that ratio is much larger. The reactants are in the denominator. So if the equilibrium constant is a very small number, at equilibrium, there are a lot more reactants than there are products, which just means the reaction was not able to make very many products before it hit that equilibrium point. So when there's a lot more products, we say that it's products favored, or it's it lies to the right. When there are more reactants, it's reactant favored, and it lies to the left. If we have a situation where we've got the large equilibrium constant, that is something that obviously we're getting more products out of that. So we would prefer to have a large equilibrium constant because that just means we're making more of what we're looking for. Okay. So I mentioned this before. When we're dealing with the equilibrium constant, we have the products over the reactants, and it does matter what the state of matter is. So technically, when we're using equilibrium constants, the standard states, the 1 molarity for solutes, 1 bar, which is a pressure unit for gases, and then solids and liquids are pure. So I didn't mention this before, but even when we plug in the numbers for the equilibrium constant expression, the equilibrium constant value itself is always unitless. So the way that works out, when we've got molarity, if we've got an aqueous solution, or bar if we've got a gas, and we plug those values in, they're not going to necessarily cancel, so we have to convert them to the standard state, which, since for aqueous solutions 1 molar is the standard state, we just take the molarity of the substance in the reaction, divide it by 1 molar. Dividing it by 1 doesn't change the original molarity, but dividing it by with the molarity, that'll cancel out the unit. So all of these values end up being unitless, which is why we have an equilibrium constant that has no units. They're always just values. So solutions, so aqueous things, we're always talking molarity. Gases, we're going to always be using bar. And pure solids and pure liquids are omitted or just equal to 1. So there are often times where we need to look up an equilibrium constant value from textbooks. They're just giant tables. But in those textbooks, they won't show every single version of a chemical reaction. So what we might see, so here's an example of just a balanced equilibrium reaction. We could write the equilibrium constant expression, the products over the reactants. So the product is the nitrogen dioxide, and the reactants are the dinitrogen tetroxide. And then here I have just the reverse reaction, where the reactants and the products have switched places. Well, in a table where we're looking this up, they would not waste the space to include both of these reactions. They would just show, let's go with just the first one, the N2O4 equilibrium to NO2s. So what if I need to know the equilibrium constant of the second one, but it's not in the table? So here the table value for N2O4 equilibrium to NO2 is 0.212. I have the equilibrium constant expression shown. So again, products NO2 raised to the power of its coefficient, which is 2, divided by N2O4 raised to the power of its coefficient, which is 1. Okay. But if I need to figure out the equilibrium constant value for the second equation, first let's write the equilibrium constant expression, so just the products over the reactants. So for the second reaction, N2O4 is the product and NO2 is the reactant. So if you look at the expressions, the above and the below, isn't the only difference the numerator and the denominator are flipped? So basically the ratio is inversed. Well, that's how we can figure out the new value. Just take 1 divided by 0.212, which is where the 4.72 comes from. So we can manipulate equilibrium constant expressions to solve for a different version of the equation. Just keep in mind when you look at the equilibrium constant expression, whatever mathematical operation is necessary to flip between them, do the same thing to the number. So let's just do a couple more examples. So with this one, again, same, the N2O4 equilibrium NO2, 2 NO2s. But if we look at the second equation, the differences here are actually the coefficients. It's like we took the coefficients and multiplied them by 2. So I'm going to write the equilibrium constant expression for the second equation. So NO2 to the 4th power, and then N2O4 squared. So if we look at the equilibrium constant expression for the first reaction, sorry, I'm trying to get my pen. Pen. There we go. So we look at this guy. Okay. And then we look at this guy. The differences between them, this bottom one is just this first equation squared. So to calculate the equilibrium constant for the second reaction, we're just going to take 0.212 and square it. Okay. So again, the table wouldn't show both of these. It would probably just show the top reaction, but we can determine the other one. Sometimes the reaction that we're looking for isn't in the table at all, which means we have to create it by using 2 or more equilibrium reactions that we do know their information. So in this example, the equation that I'm trying to solve for the equilibrium constant for is the one next to the total equation section. So the 2 NOBRs plus chlorine equilibrium to nitrogen monoxide plus 2 BRCLs. Okay, so that's what I'm trying to make. And I can't find the equilibrium constant for that anywhere. So instead, we've got 2 equilibrium reactions above this one and this one. Okay, those two. Oh, that's pretty. And I'm going to try to manipulate these. If you look at them, if we try to add these two together, wouldn't the BR2 be canceled? Because it's a product and then a reactant. And then what's left is 2 NOBRs and chlorine on the left-hand side, 2 NOs and 2 BRCLs on the right-hand side, which is this exact equation. So obviously I can combine these two equations to solve for the one that I'm looking for. Well, in order to do that, to solve for the equilibrium constant, so mathematically with numbers, if I write the equilibrium constant expression for the total equation, just products over reactants, okay, we need to decide what mathematical operation I need to do to get this and this equal to that. Adding them together is not going to work because we'd have to have common denominators. So it actually turns out if we multiply them together, that would allow the bromines to cancel. So there's the equilibrium constant for the first reaction. Then for the second reaction, if I multiply them together, this will go away. And won't I have NO squared, BrCl squared there, NOBr squared, and then Cl2? And that's what I have left. So in order to solve for this numerically, I just need to take the two values and multiply them together. So 0.014, sorry, times 7.2, which is where the 0.10 came from. So when we're talking about equilibrium reactions, we have to deal with the Chatelier principle. This is actually pretty huge and gets used a lot. If we've got a reaction that's at equilibrium, and then we change it in some way. So it's at equilibrium, it's stable, it's good, and then we do something to it. The Chatelier principle lets us determine how the reaction will respond once it's been disturbed at being at equilibrium. So pretty much, you can see the words there, but pretty much what happens, whatever you do to the reaction at equilibrium, the reaction will try to undo that, so it will adjust in whatever way to fix how you disturbed it. So if you add more of something, it is going to shift to try to get rid of that same substance. If you take away one of the substances, it's going to shift to try to make more of that specific substance. Okay, and one way we can use this Chatelier principle mathematically is by looking at the reaction quotient. So capital K was the equilibrium constant. That ratio and that value is only true when the reaction is specifically at equilibrium. A reaction quotient Q is a way for us to keep track of the ratio of products over reactants at any point during the reaction, so not just at equilibrium, but it's set up the same way. So instead of K, it's a Q, and we still have products on top, reactants on the bottom, the coefficients, the whole numbers become the powers. Again, Q just means we can use it at any specific point. It doesn't have to be at equilibrium already. So Q is helpful to us because it lets us know if the reaction is at equilibrium at the time we made the measurements for Q, and if it's not, it can help us figure out what it needs to do to get to equilibrium. So if we have a chemical reaction, we make some measurements about the concentrations at some time, and we aren't sure if that reaction is at equilibrium yet, so we use the values that we measured to figure out Q. Well, if the Q value is equal to the K value, the equilibrium constant that I would look up from the textbook, that's telling me Q, which is right now, is at equilibrium. But if the Q value that we calculate is not the same as the equilibrium constant, clearly that means the reaction is not at equilibrium at that time. If the Q value is larger than the K value, so the right now constant is larger than the equilibrium constant, that means at the time when they made the measurements for Q, there were too many products, so the reaction needs to shift to make more reactants. So the reactants are on the left-hand side of the arrow, so it would need to shift to the left. So let's say Q is 50 and K is 0.1. Well, clearly 50 is not equal to 0.1. 50 is greater than 0.1, so to make it get to equilibrium, that 50 number needs to decrease down to 0.1, so in order to do that, it has to get rid of products, make more reactants. So oppositely, if Q, the constant I get right now, is not equal to the equilibrium constant K, and when I made the measurements, if Q is smaller than K, we need more products. Our denominator is too large, so we need to make more numerator, more products. So it would shift to the right to make more products or shift towards the products. So this can let us determine if the reaction is at equilibrium, and if it's not, what it needs to do to get there, I guess. So there's just a visual of those three scenarios. So again, back to the Chatelier principle. That's talking about we've got a reaction, it's at equilibrium, and then I mess with it in some way. So one way we could mess with it is by adding something to it. So reactions at equilibrium, I pour more of something into it. Well, if the thing that I pour more into it are products, and the point of the Le Chatelier principle, the reaction is going to try to undo whatever it is that you did. So if we added more products, it's going to try to use up the products to make them go away, because you put more in, so it makes them leave. So to use up the products, it needs to shift in the left direction. Use up the products, make more reactants. So if we added a reactant, the reaction would need to shift to the right to use up the reactants. If we remove something, the reaction is going to shift to make more of that specific thing. So if we remove one of the products, the reaction is going to make more products, so shift to the right to make more products in order to make up for that loss. If we remove a reactant, the reaction is going to shift to the left to make up for that loss. Okay. If we're dealing with heat, so basically this is us adding heat or removing heat, heating it up, warming it up, or cooling it down, sticking it on a hot plate, sticking it in an ice bath. Those are the types of things that we'd be looking at here. So reactions at equilibrium, and then I change the temperature. Well, to predict what's going to happen, we have to know if the reaction itself is exothermic or endothermic. So exothermic is when the delta H, the heat value, is negative, so it's releasing heat. Endothermic is when delta H is a positive value, it's absorbing heat. So when it's exothermic, you can think of heat as if it's a product to the reaction. So the heat would be on the right-hand side of the arrow. So if the reaction itself is exothermic, then the way it's written from left to right, it releases heat. So if we increase the temperature, that's like adding more heat to it. That's the same thing as adding a product. Well, if we add a product, the reaction wants to shift to get rid of that. So it's going to shift to the left. And then inversely, if we decrease the heat, we're like removing a product, so it's going to shift to the right to make more heat. So if it's endothermic, heat is considered a reactant because endothermic means it has to absorb heat. So in order for the reaction to occur, you have to add heat to it. So heat's one of the ingredients that you have to mix together. So if you increase the heat, that's adding more of a reactant, so the reaction is going to shift to make more products. If you decrease the heat, that's taking away a reactant, so the reaction is going to shift left to make more heat to fill that void. So here's just a quick example. So in this scenario, there's my equilibrium reaction, the two NH3s, equilibrium nitrogen and 3 hydrogens, and then what we've got here, that should really be a delta. That's beautiful. Delta H, okay, is positive 92.4. We really don't care at this point what the number is, but we know that it is positive. So that's telling me that this reaction is endothermic. And that's what's the useful piece of information coming from here. So we want to know if we add nitrogen, so the reaction's at equilibrium, and then I add more nitrogen. Well, we add more nitrogen, so the reaction wants to get rid of that nitrogen, so it's going to shift to the left to use up the nitrogen. Okay, so we added more nitrogen, we need to get rid of that extra nitrogen. So again, looking at this one, we said it was endothermic, but I didn't add the heat like I should have. So an endothermic process, heat is a reactant. I'm just going to write H, because I knew that's not going to fit. So I'm going to add H there. That just means we'd have to add heat to make this reaction happen. So if we take this reaction, it's at equilibrium, and I stick it in the hot plate to heat it up even more. That's me adding heat to this. So heat's right there. So since I added heat to it, the reaction is going to shift to get rid of that heat. So it would shift to the right, away from the heat. Okay, so if we take NH3 and we remove it, so I pull the NH3 out, then the reaction is going to shift to make more NH3 to replace the NH3 that was lost. So that's going to be to the left. It needs to make more NH3. And the last one, the pressure. So if we're dealing with the pressure, we're looking at gases. And in this scenario, I always think of it in terms of volume. So hopefully we remember from Gen Chem 1 that pressure and volume are inverse. So if you, in this case, we're decreasing the pressure, which is increasing the volume. So basically we've got a container that's enclosed, but it can expand. So we made the container bigger. So when we're dealing with pressure and volume, this is only going to be affected by gases. And what's going to happen if we need to increase the volume like we do here? We need to have more gases. So looking at this reaction, on the left-hand side of the arrow, there are 2 moles of gas. 2 gas. On the right-hand side of the arrow, there's 1 gas and 3 gases, so 4 moles of gas. So between 2 moles of gas and 4 moles of gas, 4 moles of gas are going to take up more space. 2 moles of gas will take up less space. So when we decrease the pressure, or increasing the volume, what we're saying is we need it to take up more space. So it's going to shift to the side that has the most moles of gas. So left, right, left, right.